I'd like to talk to you about troubleshooting and defect reduction in coated film. This is a big subject. Ed Cohn and I are doing a short course on this coming up in November that we've cut down to 10 hours. When we get down to 25 minutes, I think it's we're not really scratching the surface. We're more hydroplaning over the surface, hoping to find a few points of traction. But we'll see if we can find those points. I want to start by talking about how I see the difference between troubleshooting and defect reduction, talk about classifying defects, and then talk about methodologies for troubleshooting and defect reduction, how those are similar and how they're different. For terminology, I use the word troubleshooting when, for an operation where normally things are okay, but all of a sudden today they're not okay. So this is not normal. The defect isn't normal. The level of defects isn't normal. And it's for the election season, I kind of call this the Republican problem. If we could just get back to normal, we wouldn't have problems. Defect reduction, on the other hand, is when there isn't an acceptable normal. Normal is not acceptable. And often that happens because market expectations change and the quality you've been selling for years is no longer acceptable. The other place that always comes up is new products. First time you bring a new product into the plant, you almost always have a whole bunch of defects in the film. Well, you got to get rid of them. You got to figure out how to make a high quality product. So there are a lot of similarities, but also some significant differences between these two scenarios. And like I said, that's what I'm going to talk about today. So let's start with troubleshooting. OSHA requires you to record safety incidents. That's a law. There's no particular laws on quality, but I think as a best practice, you ought to record your quality incidents too. You want to document the incident and its resolution. And I suggest that you use what I call a diagnostic database, and I'll explain what I mean by that term going forward. But that database becomes an engineer's reference tool. And that has become more and more important as turnover has gotten higher and higher. And these days, that's one of the big problems we have in industry is it's hard to get people to stay in a job for 2 years. So what's in a name? Most operations give defects names. Operator comes down from the line and says, hey, we got craters. Okay. And that can be very useful for communications, including with customers. But it's not useful if you get the diagnosis wrong. If you go into your doctor and say, doctor, I believe I have a strep throat, and he gives you a prescription for that strep throat, that's great until it turns out you have mono, in which case it's not going to help you at all, right? So you need to get the diagnosis right before you give the prescription. So if you're going to have a database, you do not want to key the database on the names that people give to it. You want to key that database on categories and attributes, classes. So, for example, contamination would be a category of defects. Something like pepper or speckle are specific defects. And the goal is to build links, not silos. So you want to structure the database with keys that are at least a couple levels up from the individual names of defects. Here's a classification scheme, a very simple classification scheme that I put in an article in Converting Quarterly, first quarter. And I'm not going to talk about it now. I am going to mention that, number one, it is basic. Depending on the markets you're in, you may need to have a whole lot of other classes of defects that you look at, other categories. But, for example, contamination. I mean, you're looking, is the defect made out of the same thing as the coating? Is it one raw material in the coating, or is it something that doesn't belong there? So that's sort of a general attribute. Then under contamination, you might have white contamination, dark contamination, fiber contamination, et cetera. So for troubleshooting, operators need a set of standard operating conditions that they run by. They also need a troubleshooting guide. And that should list actions they are empowered to take, things like change filters or shim the slot. They should document their efforts. In my experience, operators are very good at documenting their efforts in their own notebook, which they stick in their pocket and don't share with anybody else. The key here is to get them to share with everybody else so that you can leverage those for best practices. But operators need limits. Troubleshooting get expensive, and if it's more than something normal, they need to call in somebody else to help them. And typically that's maybe a foreman, but often an engineer. Troubleshooting guides should include mechanical as well as quality issues. I'm not talking about those, but they belong in the guide. They should describe the common problems and the actions to alleviate them. They should have cautionary information, and they should have limits because operators need limits. I don't think the operator's guide should go into science. There are other places for that, but I think it should include a coding window. Now, we're all used to these sort of cartoony, generic coding windows. Here's one for slot die with vacuum assist. And a diagram like this can be helpful to operators in saying, geez, I'm getting this defect, I should raise the vacuum or whatever. But I think what's even more useful for operators is if they have the actual coding window data, the numbers and the data points of which were good and which were bad that were done in the original scale up. That way they can look at the coding window that they have and see if that's changed from when this product was scaled up. In terms of published troubleshooting guides, there are a ton of them on the internet. There are 2 books, which I think every organization should have. Cohn and Gudoff is specific to the coating and drying process, and so that's the most germane to what I'm talking about today. The book by Dwayne Smith et al. It covers film casting to winding, actually covers paper making to winding too. And so it has a much broader scope. It's not as focused, but it has a bunch of stuff in it that is not in the Cohn and Gudoff stuff. So I think really you want to have both books available. There are limitations to these guides. I was one of the chapter editors for the Tappy book, and we would talk about a defect, and somebody would say something, someone else would say something, the line would go dead, and someone would say, well, that's all we can say in public. So other than a typo or two, the information that's in that book is not really wrong, but it's very often incomplete, and incomplete can be misleading. Cohn and Gudoff is more scientific, but the biggest issue in applying these guides is people tend to read through, and then it's like reading one of these medical books that, if you have these symptoms, this is your disease. Say, oh, that's what I got right here. And then they run off and they start taking the prescription for their strep throat when they actually have mono, because they don't test. They don't follow up to find out what it is they really have. So if the operators can't do it, they're going to call on somebody like you. And the first question out of your mouth ought to be, okay, what's changed? When did the defect appear? What else changed at that time? Is a new lot of raw material, probably the biggest source of process upsets. The key is to be efficient and be quick. I mean, these are questions you ask in the control room, not in a meeting that you arrange in the staff conference room at 2:00, right? This is very real time. Now, there are a lot of people that don't like asking a whole bunch of questions. They would much rather start turning knobs. And those of us who've been around for a while all have experiences where we got, patted on the back at the morning meeting the next day because of our quick action to turn a knob and fix a problem. But those of us who've been around for a while also have a lot of stories that involve the phrase, well, then in the second day, we started looking at some different things. And that's the problem, is if you're not disciplined about troubleshooting, you can spend a lot of time, line time, which is expensive, and waste a lot of raw materials trying to troubleshoot a process. Now, the next thing you should do after you've asked those basic questions is start characterizing the defect. So, for example here, if you have a regular repeating defect that repeats in the machine direction, generally speaking, that comes from rotating equipment. Rolls, bearings, drives, pumps, gears if you have them. They could come from building vibrations or something, but generally speaking, it's rotating equipment. And so you ask these questions, and that's how the doctor gets towards, maybe you have mono, not a strep throat. Now, in contrast, if you have something like a regular repeating TD pattern, well, that could be in the coder or the dryer. Well, but you see it at the coder. Well, those are almost always from fluid mechanical instabilities in the coating bead. And so these kinds of questions are the questions that lead you to the actual diagnosis, or fairly close to pinpointing what's wrong. Does it always work? No. Some of those categories you get in there are kind of unexplored, and it's okay. So I'm in this little box, but I don't know what that means anymore. Oftentimes changes occur between runs. So just what changes doesn't really help, because August was a great production. October is a disaster. They're all different lots of raw materials. You got to look at what's changed. And you may not have the option to change back. Like if the machine was changed in a shutdown, well, that's what's done is done. And a lot of times you have things like only one lot of bases available. And well, so you can't go back to the good base. And so now you have to resort to more powerful, but also slower techniques, which are the ones that we use for defect reduction. Before I pitch my product, I want to say that there are a lot of commercial products out there. Pretty much any consulting firm has a defect reduction strategy that they pitch. Some of the common ones are Six Sigma. Every Six Sigma project is different, but when you do Six Sigma training, I am a certified Six Sigma black belt. They say, well, look at a 70% reduction in defects. There's a discovery-driven planning model, which is very similar to what I'm going to talk about next. And then there are a number of statistical methods that are used. There's a company called QualPro that does a multivariable testing. It's a high dimensionality screening test. There's a statistical practice called evolutionary operations, or EVOP, which is very famous and very powerful, not fast. But all of these statistical methods are pretty much focused on current technology. They don't naturally lead you to when you have to actually make changes to the current technology. But there are a lot of things out there. Now, without further ado, what I generally use is what I call mechanistic hypothesis testing. And it's a 7-step process. You interview all the relevant parties, operators, managers, engineers, scientists, marketing and customers if you need them. But you brainstorm the mechanisms. How does this actually happen? You document all the hypotheses. Okay, for that to happen, this would have to happen, or this would have to be happening. And then you brainstorm, how could you test that? And sometimes that's as simple as looking up paperwork or doing a quick engineering calculation. Sometimes you have to do a little bit of lab work, and sometimes you have to test it on the line. And I think that's the big difference between this approach and the let's turn knobs approach. The let's turn knobs approach, you do everything on the line, which is expensive. A lot of the stuff can be looked into offline at a much lower cost. So those are all the things you can look at. Then you have to prioritize what you're going to do and come up with an action plan. And you test the hypotheses in order of priority to identify the mechanism. Now that you know what's causing it, then you go back and look at how could you solve it. And you brainstorm those and you test the solutions. You might winnow the solutions a little bit too to get the acceptable ones. And then step 7, which is in bold, is document what you've done. Now, sometimes you don't get there the first time through, and you may have to iterate. You go back a few times, 2, 3, 4, 5, 6 times. And sometimes you'll see continuous progress as you do this, but sometimes you have to go a lot of times around that circle before you finally get to a better place. So let me give you just a made-up example. So you've got a new film, first time in the plant, boom, you got clear spots. Well, so you sit down in the control room and people say, well, it could just be gels. Might be repellencies. We had some oils on the base lately, and somebody else, well, we had slitter dust on the base is what we had. Maybe it's bubbles from entrained air. Maybe it's blisters or from also known as solvent pops. So how do you start testing this? Well, gels can be seen in a microscope. And in my opinion, every coating line should have a microscope, whether it's in the control room or the control lab next to the coating line. But you ought to have a place you can go look at your defects and say, that's not a gel. Okay. Other tests, though, might have to send it off for a lab and it might take a week. So you open an entry in the database and you won't be able to read this in slide spiel /feed loop, but don't worry about it. It's the same database that we talked about before, but there's some squares in yellow, meaning some of those tests aren't going to be back for a while. That's okay. You still have a working document that you're filling in. Now, when you do that, the other thing you need is you need to keep track of the action items. And here I recommend doing them in, they're the ones you haven't gotten to, or in white maybe. They're organized by hypothesis. Like the first hypothesis is gels. You looked in the microscope, they're not gels. Great. That's green. That's not your problem. And a lot of times the tests that we run are not really definitive. Doesn't look like it. I don't think it is, but it doesn't say it's not. On the other hand, sometimes you get things that absolutely say it's not this, and sometimes you get things that say it absolutely is that. So in this case, we're going to pretend that the initial screen says it's bubbles in the mix. Okay, because we go forward with that. Now, we know what our mechanism is. What are our, how do we confirm that? That's the initial screen. It says those are bubbles in the mix, but until the proof of the pudding is in the plant. So you run a pilot to confirm the diagnosis. Well, let's say someone says you can vacuum deaerate. Great. But the tank's an open vessel, so you can't do that. So you pull off a 55-gallon drum, you can deaerate that, you put a closed top on it, coats like a dream. Okay, so there's bubbles in the mix. Now you really have a confirmed mechanism. And you have sort of a solution, but 55-gallon drums are not a long-term solution, right? So then you go back, and the next thing is, why are there bubbles in the mix, in the tank? And there's another round of hypothesis testing, and there may be a few rounds of that. Then you say, okay, so what would we do to prevent bubbles? Maybe we have to buy a deaerator. Maybe we need to upgrade the process to avoid introducing bubbles, or maybe reformulate the product, whatever. So this is where there's a difference. If you're troubleshooting, the 55-gallon drum might be enough to get that order on the truck by Friday. And you got to do that. If you're really doing defect reduction, the 55-gallon drum is not going to cut it. So then you got to look at the other options. Now, we talked about things like a deaerator. Well, that's capital. It's also real estate. That's a big decision. And the business has to get their arms around that. So that brings us to the goals for defect reduction. Number one, you want to confirm the mechanism. The more detailed that mechanism is, the better. Number two, generate options with an S to eliminate the defect. The more viable options, the better, because the business might not want to spend the money to rebuild the whole plant, right? They might want to you tweak the formula. If you go through this, it can take a while. It can cost some money, but reductions of 3 to 4 orders of magnitudes in defects are not at all unusual. I've worked with a lot of defects where we had 2 or 3, multiple defects per square meter. Some of them we had dozens of defects per square meter, and we got them down to where we had fractions of a defect per 1,000 square meters. Sometimes, 0.0 something per 1,000 square meters. We've gotten rid of a few defects that, maybe they're in the 5, 6 order of magnitude reduction, but in that range, it's really hard to get enough. It's really hard to do statistics. But if we look at how this mechanistic hypothesis testing plays out for troubleshooting versus defect reduction, troubleshooting, you do tend to focus on just changes. What's changed that we can change back? Typically, you do 1 or 2 rounds. How could we compensate? It's short term, very often one day, but sometimes you have lab results that are going to take a week, and you want to jump the schedule and go on to the next product, whatever. It can be sustainable too, but only if you document it. As far as defect reduction, the focus is really on causality. What's the fundamental mechanism by which this defect occurs? And it can take a lot of rounds. It depends on the problem. That can take months. And if you're looking at capital, you got to look at basic data. You got to go get quotes. You place an order, there's the lead time, and then, by the way, you got to wait to put it in and shut down. And that can very easily run over a year. But, of course, if you have a capital solution, the sustainability is literally built in. So, in conclusion, to me, troubleshooting is, if it ran well before, what changed, and try and change it back. That's usually a matter of record keeping, detective work, and sometimes some hypothesis testing. But please keep records for the next time and use your database. For defect reduction, if it was never good enough, you need to figure out what changes, what changed. You need to figure out what needs to change. You need to seek mechanisms, test hypotheses, and it's going to take time and money, but it can pay off very handily if you have massive reductions in defects. So with that, I will thank you for your attention and look forward to your questions later.